We've already seen how we can put numbers and we can plot them on the Argand diagram, just like plotting points on the number plane. We've also now seen that another way of talking about the point is instead of calling it by its coordinates, we talk about its distance to the origin, modulus, the angle it makes with the axis argument. Okay? Let's look at some fun things. We're now going to call them as a vector rather than a point. Okay? What do I mean by that? Well, here's my point. We know it has coordinates xy. It is the complex number x plus iy. It has a unique point. If I was to move that point anywhere, it would become another complex number. It would no longer be the same one because it would have different coordinates. The advantage of a vector. If I now think of it as that red line has length and it makes an angle with the horizontal. Right? But I can move it. If I move it there, its length is still the same. The angle it makes with the horizontal is still the same. So it still represents the same complex number. And it doesn't matter where I put it, it's always going to be the same complex number. It's over there, still got the same length, still makes the same angle. Doesn't matter where I put the vector, it is the same thing. Okay? The length doesn't change, the angle doesn't change. How do I work out which complex number it is? We look at the endpoints and subtract. And we say the head minus the tail. And that's why on a vector, you'll see an arrow usually. So you know which is the head, which is the tail. Obviously, if you go one way, let's look at the one that's joined to the origin to show you what I mean. The head is x plus iy minus the tail, which is 0. And so in this case, the vector's in the perfect position where it actually lands on the particular coordinate. If I was to go the other way, I'd say 0 minus that. Obviously, I get the negative of the point I'm talking about, or the complex number I'm talking about. So how do we add and subtract using a vector instead of algebra? Okay. So there's a point, Z1. And I've joined it up to the origin so I can create its vector. And there's another point, Z2. So I've now got a blue vector and a red vector. And if I want to add them, I simply place them head to tail. I put the head of one on the tail of the other, or vice versa. There you go. So that green vector would be Z1 plus Z2. So I slide the vector along and it tells me the new answer. Of course, as you know, addition can be done in any order. Z1 plus Z2 should be the same as Z2 plus Z1. So if I move the red one, sure enough, I end up on the same point. In fact, I end up with a parallelogram. Right? To subtract, then instead of placing head to head, place head to tail. Instead of saying head to tail, go head to head, because now what you're really doing is adding the negative vector. Remember how I said if you read it the other way, it becomes negative. So that would be Z1 minus Z2. I've slid the blue vector, but instead of placing the tail on Z1, I've placed the head on Z1. And I end up with Z1 minus Z2. So the black vector is Z1 minus Z2. And it doesn't matter where I put that black vector, it's always Z1 minus Z2. But there's a really interesting place I can put that black vector. Where do you think I'm talking about? So, yeah, the other diagonal. Right? Has to be, because remember I said it's head minus tail. Look at the black vector when I place it there. Z1 minus Z2. Or if I read it the other way, Z2 minus Z1. Okay? So the two diagonals of that parallelogram, in physics I think they call it the parallelogram of forces when they draw these vectors up, because they use vectors for forces. But the two diagonals, one will be the addition, one will be the subtraction. Okay. This brings up the triangular inequality. It's something you've known whether it's ever been formalised, but if you think about it, in any triangle, you can pick any side and the length of it will be shorter than the sum of the other two sides. Because the shortest distance between any 2 points is a straight line. Okay. So if I now look at triangle ABC, which is not labelled, equality will occur. ABC, let's pick a triangle here. Let's say I'm talking about Z1 plus Z2, Z1, and the blue one, remember, is representing Z2. So the length of the green vector will be bigger than the length of the blue vector plus the length of the red vector. And so what does that prove? That proves that the modulus of Z1 plus Z2 must always be less than or equal to, if they were in a straight line, they would be equal to, the modulus of Z1 plus the modulus of Z2. Okay. So that's what I'm saying there. If I look at that particular triangle, and I could rearrange that, of course. I could pick any of the sides and do the same thing. I could also say the modulus of Z1 would be less than or equal to the modulus of Z1 plus Z2 plus the modulus of Z2. Any side in a triangle will be less than or equal to. So if you ever want to prove that, it is okay to just quote it as the triangle inequality. So when you want to put some sort of reason or justification down, you can just simply say the triangle inequality. All right, let's just have a look at that again. So here we are, addition. I've got three vectors there. C would represent Z1 plus Z2. It's the parallelogram, and you've got the diagonal in there. And sure enough, if you were to slide OB over, and it would become AC, that would be the addition of those two vectors. Subtraction, a little bit trickier. There we go. D would represent the vector minus Z1. And E would then become Z2 minus Z1. I've slid that negative vector and joined it up to B. Another way of thinking about that would be to slide the vector OA, but place it with the arrowheads together. And again, I would end up over here. Note, AB is the modulus of Z2 minus Z1. And the alpha, where did I place the alpha? There it is. Alpha is the argument of Z2 minus Z1. It's the angle it makes with the horizontal. All right, let's look at a question then. This is a nice one to show you what I was talking about with the triangle inequality. They gave us this diagram, P and Q. They represent complex numbers Z and W. And just to help you out, they say, thus the length of PQ must be the modulus of Z minus W. The vector is head minus tail. The length of it would be the modulus. You could have also said W minus Z, of course, because we're talking about absolute value. It doesn't really matter which way in this case. They want us to show that the modulus of Z minus W is less than or equal to the modulus of Z plus the modulus of W. But of course, if I draw in that vector, I create a triangle. I can just use a triangle inequality. Any side in the triangle is going to be less than or equal to the sum of the other two. So you need to explain it, of course. You can't just write down the answer because they're saying show that. It's like, yeah, well, how did you get it? So I just said, oh, well, the length of OP is the modulus of Z, length of OQ is the modulus of W. They told me the length of PQ. So therefore, using the triangle inequality, I can say any side is less than or equal to the sum of the two sides. Okay, they now want us to place a point R on the diagram, which would be Z plus W, which easy enough. We just slide one vector or complete the parallelogram if you like. So let's pop it up there. And what can be said about that quadrilateral? Yeah, I already said it anyway, but out of nature I automatically called it that. Yeah, quadrilateral's got to be a parallelogram. So OPRQ is a parallelogram. Here's an interesting question. If the modulus of Z minus W is equal to the modulus of Z plus W, what can be said about W divided by Z? I hope I redrew the diagram, did I or not? Well, they've told me the diagonals are equal. Okay? The diagonals are equal. What shape has diagonals equal? Remember, it's a parallelogram. It's a parallelogram, but we now know the diagonals are equal. Okay, square, rectangle. Can we, anything, is that the best we can do? I think it is. Rectangle is probably, square of course is more information. We want the least level, I suppose. The best we can say, we can't say it's a square because we don't know the modulus of z equals modulus of w. But we can say it's a rectangle because we know the diagonals are equal. Okay. So we now know OPRQ is a rectangle. Therefore, the argument of w minus the argument of z must be 90 degrees. Okay, look at the diagram. Argument of w would be the rotation to get the vector w. Argument of z is the rotation to get the angle z. What's left is the angle in what we've just called a rectangle. Got to be 90 degrees. But we also have a rule that says when we subtract the arguments, we divide. So we now know the argument of w divided by z is pi on 2 or 90 degrees. What does that tell you about w on z? Yeah? Perpendicular, okay, but more interesting than it's perpendicular. Think of the diagram. Where is it? Close. Not necessarily I. Could be 2i, could be 3i, could be 4i. What we know is it's going to be on the imaginary axis. So w divided by z, we can say, is purely imaginary.
Could you explain that?
So, well, all right, let's go back to the picture. It's easier if I've got the picture. Right? So that angle there, PO, well, let's call it X, POX, that is, which one was P? P was Z. So that is the argument of Z, that angle in there, yeah? Okay, QOX is the argument of W. So this angle QOP is the difference in those two arguments. But we have said this shape is a rectangle. Therefore, angle QOP is 90 degrees or pi on 2 radians. Okay. So let's move back to here. So we now know that that's pi on 2. But we had a rule that we saw how to deal with this. If we subtract arguments, it's like dividing the complex numbers. So we're now saying the argument of W on Z is pi on 2. If I was to place it on the Argand diagram, I have to place it somewhere where its argument is pi on 2. In other words, the angle it makes with the x-axis is 90 degrees. So there's only one line I could put it on. I could put it there, then the angle is 90 degrees. I could put it there, the angle is 90 degrees. I could put it there, the angle is 90 degrees. But there's only one place I can put it, and that is on the imaginary axis. So it is purely imaginary. I can conclude that about W divided by Z. It has to be purely imaginary. Okay, multiplication. All right, we saw this rule yesterday. I can multiply in any order. Oh, yes, sorry? W divided by Z would have to be in the positive one, wouldn't it? Because we got an answer of positive 90 degrees. If it was the other way around, if it was Z divided by W, then we'd get an answer of negative 90 and it would be underneath, wouldn't it? Yeah. I think that would be good enough myself. But if you wanted to add that in, you could, of course. Yeah. All right, so we saw that. We can multiply in any order when we're working out modulus. And we saw that the argument, and that's what we just used basically in reverse, it was the negative one, but we know the plus. So multiplication, what's going to happen if we think of this as vectors? Okay. So let's put it into r cis theta form and just investigate here. We know that. So what has happened? If we multiply Z1 by Z2, the vector Z1 is rotated, so our new vector, we add the angle of the second vector. So we rotate it anti-clockwise by theta on 2. That at least gives me the position of the vector, where to place it. How long it is, well, I need to know the length by multiplying the length of Z1 by the length of Z2, and that will tell me how long this new vector is. So multiplication is when we rotate anti-clockwise. Or it could be clockwise if we're multiplying by a negative angle, I suppose. So let's put that in a little bit more context. There's Z1. If I was to multiply Z1 by some complex number, let's make it easy and give it a modulus of 1 at this stage. So I'm just going to multiply it by cis theta. Then it has the effect, our new complex number B, which is Z1 times cis theta, its length is the same, but it's moved an angle of theta, the argument of what I'm multiplying by. So I've added that argument onto the original vector. And what I've just put here is, well, if its modulus wasn't 1, then its length would be multiplied by r, whatever the length is of what you're multiplying by. The multiplication by I, talked a little bit about this yesterday, but it is important. Cos pi on 2 plus I sine pi on 2 is I. So IZ1 will rotate anti-clockwise 90 degrees. And if you remember when we first looked at the Argand diagram, I put that one in there. If we multiply by I, that point moved 90 degrees. Multiplied by -1, it moved 180 degrees. Again, it's all to do with you're multiplying by and you're adding the angle of the number. And the angle, if you're multiplying by -1, the angle is 180 degrees. So it moves 180 degrees. Multiplied by I, it's moving 90 degrees. So multiplication by I, rotation anti-clockwise by pi on 2. Always keep that in mind. If you want to work out what the actual complex number is, head minus tail. Whatever the endpoints are, subtract them. It'll tell you what complex number the vector is representing. So, here's a little question. Drawing a shape there. I think it's a square. I haven't actually said so, but from memory, for this problem to work, it actually is a square. So use your imagination. Scales out a little bit. That's a square. Okay? Now, what do I know? If that's a square, and this is how we write vectors. Okay? We write down the endpoints, and then we put an arrow on the top so we know which one's the head, which one's the tail. So C is the head, D is the tail. So we're going tail to head, direction of the vector, DC, like that. So what I'm saying is, the vector DC, if I wanted to get that, it's the vector DA rotated 90 degrees. Remember I said this was a square. Okay. So if A is W, or omega more correctly, I've got to be careful here. I want to work out the point C. Remember, a vector represents head minus tail. So if I substitute in to try and work out the point, I've got to substitute in head minus tail. So vector DC is C minus 1. And it will equal dA. Well, that's omega minus 1 times by I. So now I can work out what point C actually is in terms of omega. Rearranging that, making C the subject, so it would be 1 minus I plus I omega. That would represent the point C. If I want to work out B, okay, I could say, well, to the point A, I'm sliding the vector CD or up, or DC up. So I'm saying to the point A, I'm going to add the vector DC. So the point A is just omega. That's going to end up being the endpoint. And then plus C minus 1. We said this vector was C minus 1. C we've just worked out. Mind you, to save a little bit of time, rather than putting in that one, I subbed in, didn't I? I factorised it a bit. Yeah. There it is. Another way of working out B. I could have said it's C plus the vector dA. Another way of saying I've got the point C, I'm going to add on the vector dA. So C, we now know to be that point. I'm going to add on dA, head minus tail, which is omega minus 1. Expanding all that out and tidying it up, I come up obviously with the same number.
Why did you leave the eyes grouped together? Like, why did you
I don't know, it doesn't really matter, I suppose. You could have written it, yeah, in terms of real and imaginary, yeah. Yeah. I suppose I'd put it in terms of, oh, well, it's some multiple of our original one and then I've added something. So that was my thinking in my head. But yeah, you could have grouped it real and imaginary. Yeah. Another way I could work out B, if that's a square, then I know this. I could rotate the vector dA 45 degrees. And it would be in the right position now to land on B, because we know the diagonal in the square would be 45 degrees. But the length would change. But because it's a square, that means that's a 45 degree right angled triangle, and I know the sides are in the ratio 1, 1, root 2. So therefore its length would be multiplied by root 2. So root 2 cis pi on 4 times the vector dA. Remember, cis means cos plus I sine, so I can actually calculate this out. dA we've worked out is omega minus 1. Well, cos pi on 4 is 1 on root 2, so is sine pi on 4. So we end up with 1 plus I times omega minus 1, then moving the 1 to the other side of the equation, we add 1, and playing around with it, eventually, again, we get the same answer. So it's just how you're thinking about it at the time. Did I slide a vector? Did I rotate a vector to get where I want? It should all work, no matter which way you pick. So the 2000 paper. In this case, we're told it's a rectangle. And A is omega. And the sides of the rectangle, the length is twice the width. The first part of the question says, well, what point is C? Well, all I know is a rectangle, and its length has been multiplied by 2. So therefore, the vector OC will be the vector OA. It's rotated 90 degrees, so that's multiplication by I, but its length has been doubled, so it's multiplication by 2I. Well, OA, I know, is omega minus 0, which is just omega, so C must be 2I times omega, whatever that works out to be. All right, what complex number corresponds to the point of intersection D of the diagonals OB and AC? Well, I know the diagonals will bisect. So that point of intersection must be the midpoint of AC. All right. Midpoint formula. What do? We add the points together and divide by 2. It's just that I don't have coordinates x, y, but I know when I say add the points together, I'm going to add the x values together, I'm going to add the y values, divide by 2. So it's A plus C divided by 2. Well, A was omega, C was 2I omega, and I'm going to divide it by 2. So I could write it like that. Whatever omega turns out to be. Obviously, I can't work out the coordinates because I don't know the actual coordinates of omega. But it would be a half plus I times omega. So another example. OBA is an equilateral triangle. To make life easy, they've told us the length is 1. OBCD is a square. We want to find the points B, D, and C. When they ask a question like this, use your head. Why didn't they say find B, C, and D? Because it's probably going to be easier to find D before C. Right, so they're giving you a subtle little hint there. I mean, you don't have to do it that way, but let's see what happens. Okay, let's find B. The vector OB would be the vector OA. They've told me it's an equilateral triangle, therefore that angle is 60 degrees, or pi on 3. So this time I've rotated pi on 3. So multiplication is just pi on 3. OA is simply 1. They gave it to us, yeah. Yeah, it's a very old question. It was a handwritten diagram, and yeah. A must represent the point 1. It's on the real axis. Its modulus is 1. So it is the point 1. So I actually know which one that is. I'm going to multiply it by cis pi on 3. So in other words, I just got to work out cis pi on 3. B is the point, a half plus root 3 2I. Okay, I'm going to use the subtle hint. So to get the vector OD, I'm going to rotate the vector OB 90 degrees, multiplication by I. So if I multiply B by I now get minus root 3 on 2 plus a half I. So now I just have to work out C. Well, I'm going to say C is the point B, but to the point B, I'm going to slide up the vector OD. So I'm going to add that vector in. So B was a half plus root 3 on 2I. OD, head minus tail, well the tail is 0, so it's just going to be minus root 3 on 2 plus a half I. Adding that all together, there's C. 1 minus root 3 on 2 plus 1 plus root 3 on 2, I. All right, let's do another one. Yes, I know there's a lot of examples, but you know, we need to get our head around this. Okay, we've got this really interesting diagram. They want to know why P corresponds to the complex number 1 plus I Z1. Well, they've told me those vectors are equal and the angle between them is 90 degrees. So I've said AP is AO times minus I. Because in this case, I'm saying I'm getting the vector AO and rotating it anti-clockwise. So it would be cis minus pi on 2. Because remember, it's not the complex number that's negative, it's the argument that changes to negative. But in this case, it has the same effect of multiplying it by minus 1 because we're talking about I. So it's cis minus pi on 2, which is minus I. I could have done it by saying I've got PA, and that would times I gives me OA. I could have done it that way as well. But I suppose because they're asking to find P, I made AP the subject. It's the only reason I did it that way. So all right, let's sub in what we know. AP would be P minus A, and AO, and this is where I've got to be careful because it's so easy to say A minus O out of habit, but in this case it's actually O minus A. You rotate at the tail. So you always rotate at the tail. A is the tail in this case. So sub in what we know. A is Z1. So when we rearrange it and then factorise, there it is. 1 plus I times Z1. Okay, part 2, which is labelled part 3 for some reason. Let M be the midpoint of PQ. I suppose there might have been an original part 2 saying find Q, but don't know why it's done like this. But because obviously I'm going to have to find Q to work out the midpoint of PQ. So a similar sort of idea to the last one. If I look at the positioning there, I can say, well, vector QB, to get that one, I'm going to rotate BO, but this time I'm going anti-clockwise, so it's multiplication by positive I. Q minus B is I times 0 minus B, so we get B minus IB, so I have 1 minus I times Z2. Midpoint, add them together, divide by 2. So I get that out. I mean, I could leave it like that, I suppose. I think this time I did put it into real and imaginary. Yeah. So I've got Z1 plus Z2 plus Z1 minus Z2I all over 2. All right, let's take a breath. Okay. Cambridge, fictional Cambridge, 1E. And this time, not a Patel exercise, and I've put these photocopies in there. The Terry Lee exercise, I don't mind on this. So 2.6. Wow, how long was that one? Woo! That's going to